Okay, in this video, we are going to introduce the concept of error and uncertainty. And essentially, this is going to become the basis for answering the question, how good is the result that we got from measuring something? And so, as a review, the most important things that you can take away from this course are number one, how accurately do we need to know what we're measuring? And then number two, how accurate can we be with the instrumentation that we have available to us or that we have selected? And then number three, what is our confidence in the result that we got based on our measurements? And then number four, what is the interpretation of the data that we've collected, or what is the data telling us? So then as engineers, we can actually make informed decisions for our design that we're working on based on measurements that we have taken.
So if you think about the overall perspective of this class and you keep those things in mind, error and uncertainty analysis is at the root of it. And so that's why we're going to spend a fair amount of time talking through error and uncertainty. And then we'll get into how do we work through that and calculate out what the uncertainty for the different measurements are. So with that, we will step into a problem to solve. So the problem that we have is a brass rod repeatedly loaded in a fixed tensile load, and the axial strain in the rod is determined with a strain gauge. And so it's okay if we don't know what all of these things mean. By the time this class is over, you will know exactly what all of these things mean. So we take 30 results under fixed test conditions, yielding an average strain of 520 microstrain. Now, statistical analysis of the distribution of the measurements give a precision uncertainty of 21 microstrain at a 95% confidence level, and the bias uncertainty is measured to be 29 microstrain with odds of 19 to 1, which is 95% confidence. Okay, so what is the total uncertainty of the strain? Now, one might think we just add those two numbers together and we're done. So we got 21 plus 29. We're engineers, so we realize that things are probably going to be more complicated than that. So let's dive in and put together the tool set that we need in order to solve this problem. In order to do that, we need to first start out with classification of measurement errors. So how do we classify them? So first off, how is error defined? Well, you've got an equation here, which is the error is equal to the measured value minus the true value. So the true value is what we're trying to find out. Is that 40 psi? Is that 6 feet? Is that 14 micron? And so the question here is, how wrong is our measurement? The error is how far off is our measurement from the true value, okay? Now let's talk about uncertainty for a second. Now uncertainty is a little bit different than error in that it defines the bounds that would contain the correct value. So now we're saying we've got some bounds on either side of the true value or the correct value. And if we have those bounds on either side and we say we've got a 95% confidence that our true value, the real value, is going to fall in between those 2 points. And so that's kind of what this equation right here is showing, is we've got a minus uncertainty in our error and our plus uncertainty. So we've got these bounds saying the true value. So if we take this equation here and plug it in and rearrange, we say the true value is somewhere in between these two bounds with this specific confidence, okay? All right, so here are some examples of error. We've got random or precision errors. So when I use these terms, I'm going to use them synonymously throughout. We've got a random error, which is also a precision error. So these are random things happening. And so you can see this little target down here. They're just randomly hitting around at the actual value or the true value or the target in this case. So the readings are just all around. Now a systemic or a bias, these are going to be offset by a specific amount every single time. So something is causing this bias. So let's go back to the precision side. They're not consistent in occurrence. And so variations caused by instruments or the operator. So there's a lot of things that can cause random or precision error. And some of those examples would be like air currents. So if somebody opens the door and wind blows off of that door and you're doing a very fine measurement of the wind velocity, that is going to be a random event that causes a change. Temperature variations during measurements, inconsistencies of objects being measured. So like if you picture measuring a brick, it's not going to be uniform along the side. And so if you measure it in a bunch of different locations, you're going to have different thicknesses or measurements that you take. And so that's the same kind of thing. Human parallax error, that's when you're looking at, say, a tape measure and maybe you don't have it directly lined up on top of, and so you're looking off to one side and so you can see, or maybe your speedometer or your gas gauge. Okay, so systemic or bias errors, they are clustered around an incorrect value. So they're inherent to the system. And so these errors are due to, say, poor calibration or no calibration. There's a zero offset or a scaling factor. And so because of the instrument, you're always going to have an offset.
Okay, so as a quick introduction to uncertainty bounds, I just wanted to give a couple of very simple examples of a digital and an analog measurement device. So on the left-hand side, we have a guinea pig sitting on a scale, and the guinea pig weighs 261.3 grams. And so the uncertainty bounds that we have on that essentially are going to be the smallest division because we don't know what's happening between 261.3 and 261.4. And so really, with this measurement device, we can't confidently say that it is 261.35. We can't tell what's happening between those two because of the resolution of that digital scale. And so one of the subsets that goes into the uncertainty bounds that we would have on this measurement is not knowing what's happening between the resolution limits of this scale. And so that would be the smallest division is what we can confidently say we know what's happening in terms of the measurement itself. So same thing on the analog side, we have some resolution error, but it's a little bit different because if we are reading off of this measurement device over here, this ruler, we could probably guess if it's greater than half of the smallest division or less than half of that smallest division. And so you can see, and this is a pretty fundamental issue that a lot of people who are first learning about uncertainty bounds kind of get caught up on is because there's a lot of different scenarios. So you kind of have to look at each scenario and say, what truly makes sense? Can we truly guess a smaller increment, less than half of a millimeter in the case of the ruler? Can we actually guess with an accuracy or a high degree of confidence? And the answer is usually probably not. And so as we go through, keep this in mind that we're going to have these different scenarios that we're going to have to kind of split apart and really be thinking about truly what is the resolution or what is the greatest accuracy that I can get out of this measurement device. And so these are just a couple of examples of bounds. So if you were to look at this analog ruler, you would say, I have a high degree of confidence that I can tell you what's happening up to a half a millimeter. Other than that, I don't have a high degree of confidence. So that's kind of a concept that we're going to be looking at on a regular basis as we go through uncertainty analysis and uncertainty bounds.
Okay, so going back, the uncertainty analysis is how good the results are that you're reporting. And so that uncertainty is going to be some value that you've measured plus or minus an uncertainty. So again, uncertainty are the bounds at which you can be confident something is going to fall within. So again, how is error defined? Well, it's a property of the measurement. So it's like an effect. The errors cause the difference between the measurement value and the true value of the population. So errors cause the measurement value to be different from the true value. Now, uncertainty is different than error because it quantifies the quality of the result, quantifies the probable limits of the error, and a numerical value that bounds the error in the measurement. It's used to design the phase. It's used in the design phase of a project to know where to spend your money. If we need to know it with a high degree of accuracy, we're going to spend more money there. It also puts bounds on the expected values used in design. And so if you are the engineer who have come up with these bounds and you publish them, now somebody knows that they can count on your device or your material to work within a specific nominal value plus or minus an uncertainty. And so the uncertainty is really what we're driving for in this class. So again, uncertainty is the property of the result. So these are numbers that we're going to use to define an interval that will capture the data that we are analyzing. So just to recap, error is defined as how wrong is the measurement. Uncertainty is defined as the bounds containing that true value or the correct value. And we have to always include a confidence. And we're going to talk all about this. But right now, error and uncertainty definitions is what we're focused on.